Welcome everyone to the Intel Network Builders webinar program. Thank you for taking the time to join us today for our presentation titled Open vSwitch with DPDK in OVS 2.6.0. Before we get started, I want to point out some of the features of the BrightTalk tool that may improve your experience. There is a questions tab below your viewer. I encourage our live audience to please ask questions at any time. Our presenter will hold answering them until the end of the presentation. Below your viewing screen, you'll also find an Attachments tab with additional documentation and reference materials, including a number of websites and documents mentioned in this presentation. Finally, at the end of the presentation, please take the time to provide feedback using the Ratings tab. We value your thoughts and will use the information to improve our future webinars. Intel Network Builders webinar series takes place live every week, so check the channel to see what is upcoming and access our growing library of recorded content. In addition to the resources you see here, we also offer a comprehensive NFV and SDN training program through Intel Network Builders University. You can find this program at networkbuilders.intel.com/university. Today, we are pleased to welcome Ian Stokes with Intel. Ian is a network software engineer with Intel. His work is primarily focused on accelerated software switching solutions in user space running on Intel architecture. His contributions to Open vSwitch with DPDK include the OVS DPDK-Qos API and Ingress Egress Qos solutions. Welcome, Ian, and thank you for taking the time to join us today.
Thanks, Renee. Hi everybody, my name's Ian Stokes. Just to be clear, this presentation is a collaboration between myself and my colleague Ciara Loftus. Unfortunately, Ciara can't be present with us today because she's actually attending the Open vSwitch conference in California this week, so it'll just be myself presenting. And I guess on that note, what are we here to look at today? So we're going to be talking about the 2.6 release of Open vSwitch, and in particular the new features that are available in DPDK datapath aspect of OVS. So as we go along, feel free to submit questions and we'll spend some time at the end answering them. So, the agenda. A quick review of what we're going to see today. Just what we're going to review today, sorry that technical difficulty. We're going to look, just to start off, we'll look at an overview of virtual switching, and in particular Open vSwitch itself, for those of you who aren't familiar with it, or would just like to brush up on your vSwitch knowledge. Then we look at some of the new features available in OVS 2.6, starting with DPDK 1607 integration. Followed by this, we look at quality of service, jumbo frames, extended statistics, multiple vHost user updates that we've included in 2.6. We look at the pdump functionality, and finally some usability improvements. Then we'll take, just before closing, we'll take a look at what's actually going to be available in OVS 2.7, so the next release after 2.6. So, just starting at a high-level overview, what is Open vSwitch and what's virtual switching in general? So, in this slide, we can see an example of a topology network in a data center. And just to be clear, this is just an example, right? Topologies can vary. But in this example, we can see that there's 3 tiers of physical switches, ranging from our core switches, our aggregation switches, and then our top of rack or TOR switches. And so switches really, if you're not familiar, they're the backbone of communication for our servers in the network. And they also allow servers to talk to the internet. And so when we think of a virtual switch, really the best idea is to kind of extend this thought into the servers themselves, i.e. it's a virtualized data center within the server. And virtual switches allow virtual machines to communicate with one another and with the extended networks via the top-of-rack switches. And so this is kind of key when you come to NFV and SDN. So in NFV, we virtualize network functions, and so it's important that they can have a way to communicate between each other over the network also. And also you'll notice that not just communicating between each other, you also have this controller in the center, that this would be an entity that would manage different switches, including the network switch and breach switches themselves, so they have to be able to communicate with that as well also. So, if we were to look then at openvswitch.org, so what is it? So there's many virtual switches available today, varying from commercially licensed to open source. And of all the open source virtual switches, Open vSwitch is probably the most well known and deployed to date. And the reason would be, so Open vSwitch, what is it? It's a production quality multi-layered virtual switch. And what we mean by multi-layered is that it does more than just L2 switching. It can also do L3 switching and various protocols at that side. Another key advantage is that it's permissively licensed under Apache 2.0, which is quite like a BSD style of license. So it has minimal requirements with regards to redistribution. And this is a great benefit to OVS, and it's contributed, to why it's being so widely deployed and used. So now that we just have a high-level overview done, maybe we might start looking at the features that have been introduced in OVS 2.6. And to kick off in particular will be the DPDK-1607 integration. So if we were to look at something like native OVS or kernel OVS, as we call it, on the top left, we can see that this native OVS is using kernel forwarding space essentially. And I guess the idea we want to do is when you introduce DPDK, what DPDK is that it's a set of libraries for fast packet processing. It can introduce a driver. It operates in user space and has an IGBI UIO driver, which essentially allows poll mode drivers to speak to between NICs and processing libraries. And what we actually do is what OVS with DPDK does is that it moves the forwarding plane from the kernel space to user space under the guise of this DPDK library and drivers. And this significantly improves performance for a number of reasons. So we're not going to dive too far into them at this point, just in the interest of time. But essentially, we now use poll mode drivers and various accelerators that are available through the DPDK library to speed up the performance of OVS. So just one thing to note, I guess, is that with each OVS release, we try to align with the latest DPDK release that's available. So previously, whereas we would have had OVS 2.5 would have used DPDK 2.2, what has happened since then is we've now released OVS 2.6. But on the DPDK side, there's actually been 2 releases since DPDK 2.2. And not only has been 2 releases, but they also changed their naming convention. So instead of it being DPDK 2.3, it actually changed to DPDK 1604. So year 2016, month 04. And then another release came out after that saying DPDK 1607. And just to be very clear, for OVS 2.6, we integrate with DPDK 1607. So not a major point, but it's just to be aware, just in case you're wondering why there's such a version name change between DPDK 2.2 to 1604, just some background information on that. And I guess, what's the purpose of this? Well, we try to keep to the latest DPDKs, obviously, for every OVS release, because with each new DPDK release, there tends to be a number of performance increases for the NICs, as well as bug fixes, and sometimes just new features completely added to the DPDK library, which we try to leverage then in our latest OVS with DPDK release. So with this in mind, let's look at our first aspect, which would be quality of service. So originally, quality of service was implemented as part of the kernel OVS implementation, but the problem was that there was no solution in the OVS with DPDK aspect of OVS. And so this had to kind of be tackled in 2 ways. There was one, we needed to create an extensible QoS API for NetDev DPDK ports. So we mean extendable by it's not just one type of DPDK QoS that's supported, it could be others that are supported in the future. And then we also need to provide a sample QoS type. So that's what's actually provided in OVS 2.6. So under the hood, there's a new QoS API, which can be extended in the future, but we also provide the sample QoS and egress policer. And all an egress policer is it simply drops packets once a certain rate that's been specified is surpassed. And it uses a token bucket implementation from the DPDK library to do this. So at this point, it would be important just to call out that we're talking about, when we talk about quality of service in OVS, they regard quality of service as being applied to the egress traffic, or traffic that's being transmitted from the switch. And it's important to look at this from the point of, depending whether you're a virtual port or virtual NIC versus a physical port or physical NIC, this actually has an impact on which way the traffic is being sent. So when we say egress policing for NIC, i.e. you can see in the diagram, it's traffic that's being sent from the switch out to the NIC, out to the external network. That's where the packets will be dropped. When we talk about doing egress policing in terms of a virtual port or virtual NIC, essentially this will be traffic that is being sent to the guest or the virtual port that's on the guest. And so essentially by policing that, you're essentially policing the receive rate of that interface from the guest point of view. So it's just one of these things, because it's sometimes People get confused with this, but it's just an aspect to call it very clearly. That's what we mean when we say egress. It's egress from the point of the virtual switch. So with that in mind, that was the first solution we put in, which would be the Egress Qos. But the flip side of this is the Ingress side. And for anybody who's not familiar, in OVS, they treat Ingress and Egress separately. Egress is configured with the OVS Kettle toolset for QoS, but when you use Ingress, it's essentially configured using the interface toolset. And the interface toolset is referred to as rate limiting, essentially. But in this place, what we've done is we've implemented a similar feature here where you're just doing Ingress policing. It's similar to the Egress, i.e. it's a rate that's set and any traffic surpassed is dropped. To be clear, it's not buffered. It's just dropped immediately. It's identical in setup to kernel OVS. So if anybody's familiar, has set up the kernel OVS interface rate limiting, it's identical in terms of setup and commands for that aspect. And again, just as a reminder, when we say Ingress, it's Ingress from the point of view of switch. So for physical NIC, in this case, it's traffic being received on that physical NIC and being passed to the switch will be dropped. And from a virtual port, it's traffic being transmitted from the guest, and i.e. being received at the virtual switch from the guest, that'll be dropped. So essentially, you're limiting the guest transmit capability. So just as an FYI, at the end of these slide set, we have a collateral slide deck. There's actually articles on the Intel Developer Zone on how to configure and use these in some basic use cases. Feel free to go through this, and we can actually give this collateral later to anybody who's interested if you want to actually try and demo any of these new features. I'll call out as each feature goes along which ones have them and which ones don't. But both Ingress and Egress Qos do actually have this configuration documentation. It goes a little more technical than what we're going to look at today, but it might be quite useful if anybody's interested in setting this up. So moving forward, I guess the next feature we look at would be jumbo frames. So again, for anyone who's not familiar, essentially the standard largest Ethernet MTU for DPDK ports was 1500 bytes previously in OVS with DPDK. And what jumbo frames gives you is actually the ability to go above this size. And so instead of 1500, you can go to larger sizes. The solution for this kind of came in two parts again. One was that we wanted jumbo frames to be, you could set this dynamically on your ports, i.e. it's not just set when the port is created, initialized, it's dynamic. You can set it and change it as needs be. For this to be implemented, we were actually waiting for a piece of code which is dynamic reconfiguration of netdevs at runtime. So this was a dependency for the jumbo framework. So we worked with the community for that. And once that piece of code was available, we were then able to implement our new MTU implementation. And so how the main thing with the MTU really is that it's done by allowing DPDK to allocate a mempool that contains sufficiently large enough MBUFs to facilitate the size of a jumbo frame. And when we speak with DPDK, when we talk about MBUF, that's what DPDK uses to represent a packet. So on our diagram, you can see that DPDK 0 has MBUFs of 9,000, meaning that it can have a maximum MTU of 9,000, whereas on DPDK 1, port 1 would have a maximum MTU of 1,500. So it's just showing the difference. You're just giving that capability to actually configure this. So the status of this work is that it's actually submitted and is part of the OVS 2.6 release. And again, as part of the collateral, there is a very good blog on the Intel Developer Zone explaining some of the inner mechanics and the memory sizes versus just as well configuration and usage. So I encourage everybody to check that out. So moving on, extended statistics. So extended statistics, what we mean by this is that originally with OVS DPDK, we had very basic stats in terms of we could tell what was being received and what was being transmitted, but really we couldn't get much more than this. And with DPDK, we have the ability to actually read NIC registers and obtain what we call extended statistics. And this kind of gives us a really, a lower level viewpoint of what's going on with our traffic. And so OVS can now report packet size breakdowns, so your different packet sizes, whether it's multicast or broadcast packets, and it can also define, so what's oversized, undersized errors, stats on fragments, and Jabber errors also. So that's a new feature that's also been added to OVS 2.6. So next feature we look at will be NUMA Awareness. And what we'd like to do here is that before we actually dive into vHost user NUMA Awareness, I'd first like just to touch on vHost user itself and maybe give a small bit of background for anybody who might not be familiar on what this actual feature is. So in network function virtualization, a big concern is ensuring that virtual machines running in virtual network functions can be supplied with traffic at a high enough rate to ensure that the bottleneck in the network doesn't occur. And there's multiple methods of getting traffic into a VM, including, for example, you might have an SRV solution, which is more hardware focused. You might use IV shared memory, which is a software model offered by DPDK. And then there's also VirtIO.net and vHost.net, etc. However, the kind of de facto method offered by OVS DPDK is something called vHost user, and this was introduced in OVS 2.4. What it is, essentially, is a user space vHost driver whose backend is implemented in DPDK. And how it actually works is QEMU, which is running in a virtual machine, will share the location of guest virtual queues with OVS DPDK. And so if we look at our diagram, you can see at the top just the QEMU element, and you can see an RX and TX queue. And once this is actually shared with OVS with DPDK, it means that OVS with DPDK can place packets on these queues directly with a single copy in a very efficient manner. And this is what yields the good performance. So in OVS 2.6, some further improvements were made to this virtual interface in order to make it both more performant and more feature rich. And so the first of these is actually the vHost user NUMA Awareness, which we look at now. So vHost user NUMA Awareness, its feature is introduced in DPDK to address a fairly typical problem and a common enough use case. So this use case is when we have two VMs or multiple VMs with vHost user ports, and they're placed on separate sockets in our server. So in this case, our server has socket 0 and socket 1. We have VM 1 placed on socket 0 and VM 2 placed on socket 1, essentially. And what we actually do is that if we walk through this diagram, you'll see where this issue actually comes. At first glance, you can see that port 0's memory, which is all in blue, is located on one socket. But port 2, which is in green, you can see that the memory changes. And when we talk about memory, what do we mean? Well, there's three aspects of the memory we need to be concerned with. We need to be concerned with the QEMU memory, which we've just highlighted. We need to be concerned with the OVS memory, and we also need to be concerned with the DPDK memory. So you can see that these three areas, ideally they should be located on the same socket. And what we would say is that if it's configured like, if at first glance you can see as well that this is not optimal. And why? Because essentially we can see traffic is going to come up and it's going to cross our QPI bus between our actual two sockets. And this causes an issue because the QPI bus itself becomes an actual bottleneck between the two. So what the actual solution to this would look like is with DPDK, what we can now do, why this is actually a problem, I suppose, is that with DPDK previously, all the memory for a DPDK port must be managed on the one socket. And what NUMA Awareness allows you to do is work between both sockets, essentially. And so what we can do now is our DPDK memory, which is all in one socket originally, as we move to 2.6, this will now be extended so that this memory can actually be allocated to socket 1 also. Now, that takes care of the DPDK memory, but we can also just see that the PMD memory, or the PMD thread for OVS is still on socket 1. But now as we've moved our DPDK memory onto socket 1, we can actually now move our memory as well from this socket onto socket 1 also. And now we've actually relocated all three memory types onto the one socket. And so this is quite useful as it actually improves performance over the previous case because we're now avoiding the QPI bottleneck between the two sockets. Again, there's an article available for this on the Intel Developer Zone, and I would encourage anybody who's interested in this further to check that article out for configuration usage. So next aspect we look at will be vHost Client-Mode and Reconnect. So vHost User Client-Mode is a new DPDK feature introduced to address another limitation. The limitation this time was the fact that the vHost user port could not regain connectivity to the DPDK backend, in our case OVS DPDK, if it crashed or was reset. So prior to this feature, if OVS DPDK encountered a failure, the VMs attached to OVS with vHost user ports needed to be rebooted in order to regain connectivity. And this is a major inconvenience for all users, but especially it's inconvenient in a production environment where downtime of VM may mean downtime of an important service. So the vHost user model itself, why this is a problem and why it is this way, it's just some technical background. I guess it's the fact that the vHost user model itself uses a standard Unix domain socket to pass control messages between QEMU and OVS with DPDK, and this socket is integral to vHost user's infrastructure. So the reason why connectivity could not be regained when the switch failed is because in default vHost user configuration, which is shown in the diagram, we can see that OVS with DPDK creates a socket and QEMU connects to that socket. But when the switch dies, so does the socket, and QEMU is left listening forever on a dead connection. So the improvement that vHost client mode and reconnect brings is that we now move this actual connection onto the socket to the QEMU level. So with the client mode, however, it's now QEMU who creates the socket, and OVS DPDK connects to it. So now OVS DPDK has become the client to the QEMU server. And in this case, if the switch dies, it's okay, because the socket is still alive, it's managed by QEMU, and it hasn't changed its status. So from here, we can just relaunch OVS with DPDK, and it can reconnect to the socket and its connectivity, and this is regained seamlessly. And so this is a major advantage to what we had previously. And again, there's an article on this on the Intel Developer Zone as part of the collateral at the end, which I suggest people check out. So the next feature we look at pretty quickly will be the pdump packet capture. And so what this essentially is that the pdump library was introduced in DPDK 1607 to allow users of DPDK-based applications like OVS with DPDK essentially to monitor traffic passing on DPDK devices. And this wasn't possible beforehand. And this has always kind of been a gripe with the community, that if you're using kernel OVS, you can use something like TCP dump to monitor these interfaces. But when you use the DPDK, you've moved to user space. And now, you can't use TCP dump with that anymore. So this is something that we've kind of implemented to try and work around this. So you can kind of think of pdump just like TCP dump for DPDK devices. And the DPDK pdump library uses a client-server model where, so in this case, OVS DPDK would act as the server and would initialize the pdump framework. Now, at this stage, a separate secondary DPDK process must be launched, and this acts as a client. And this is responsible for enabling and disabling the packet capture. And so, for example, an existing application that can be used as the client is the DPDK pdump application. And this can be found in part of the sample apps directory in DPDK. So we can see this on the right-hand side, that the DPDK pdump essentially will capture traffic that's hooked into OVS DPDK and output it to a PCAP file. And once you have this PCAP file, you can use your favorite kind of packet viewer, so it could be Wireshark or TCP dump, and you would essentially be able to read this packet pdump, and now you can see the traffic that have actually passed over the DPDK ports. So one thing to note here is that there is a performance decrease when you use OVS with DPDK with the packet dumping monitor application, and so this feature really is more for debugging purposes than anything else. And again, this is another feature that has an article on Intel Developer Zone as part of our collateral. So, last feature we look at, is usability. It's kind of a group of a number of different features. We'll just look at it at a high level. But this is feedback that we had previously from the community that, OVS with DPDK, you really need to know the ins and outs. There's a lot of kind of gotchas that can make setting up a bit more difficult. And so we kind of put this under one umbrella for a number of different improvements that we've made. And so let's go through some of these. So I'd say the first, which was kind of really useful to a lot of people, was that we refactored the OVS DPDK installation guide. So beforehand, or before 2.6, the DPDK guide was essentially the OVS DPDK guide was one big long document, and that included everything from how to compile OVS with DPDK to how to run it, how to optimize it, etc. And it was quite difficult for anybody at the beginning. You mightn't be at the beginning, you just want to get OVS with DPDK up and running. You may not want to know how to optimize it yet. A lot of feedback was that people found that quite difficult, that it wasn't just as clear as plain as day. So what we decided to do is, with all this information, we decided to split it into two. So now we have one document for beginners and others for advanced, who wish to do more complex things with OVS, DPDK. And so, as we said, the beginner's guide is more just to get you there. Hey, this is how you set it up. This is how, it should be compiled, and these are the basic things you need to get up and running. Whereas the advanced guide now brings in things like RxQ affinitization, PMD affinitization, things that you just need to know if you want to start tuning the system essentially to get better performance. So they're kind of split into two documents, and just to help beginners essentially. So I guess some of the other information that we've also done as part of the usability guide is that we've looked at simplifying the OVS DPDK command line. This work was done by the community, and this was a typical pain point from the community point of view. And we've also implemented auto detection of the DPDK library and header files when configuring OVS. So again, it's just kind of making it a bit simpler to deploy and use in the everyday use cases. Okay, so with that, I guess that kind of concludes at a high level all the OVS 2.6 features that we'll discuss today. Just to close out, I guess a good opportunity to look at some of the potential features for OVS, the OVS 2.7 release that we can perhaps look forward to. And it's worth noting that the list we're providing here, it's not completely comprehensive, and it's not guaranteed that all these will be here, as it's to be TBD at the moment. But there is ongoing work on these features, which we're hoping to get into the 2.7 release. So first up is TSO support, and TSO, for anyone not familiar, stands for TCP segmentation offload. And it just involves making use of specific NIC capabilities to segment large TCP packets and then improve this performance. So essentially, that's one of the new features. There's kind of ongoing work for that at the moment. Then we're looking at improvements for the EMC and datapath classifier, which are being investigated. The EMC and datapath classifier are two levels of lookup in OVS, and some optimizations have been made in these areas by using techniques such as cache alignment and improvements to the prefetching and batching operations in the code. Next, what we have is the VXLAN optimizations. So they're currently being looked at, and in particular, the possibility to offload the RX checksum validation for tunnel packets to NICs that are capable of doing this on the NIC silicon itself. So that's one area we're also investigating. The vHost PMD is also being investigated, and so what this is that it's an under-the-hood change for vHost that brings the vHost user ports under control of DPDK's Ether API, and it just simplifies the OVS DPDK code path for maintainability and usability going forward. As well as that, we're looking at arbitrary port naming. It's being investigated as well. This feature essentially allows us to name DPDK ports whatever we like. Currently, right now, we're restricted to using the word DPDK followed by the port ID, which is what, that must be done for physical ports currently. So we have a patch on the mailing list that currently changes that, and we're hoping to have that in the next release, that you no longer have to use DPDK followed by the port ID. You can call it an abstract name. Another feature we're looking at is the OVS Keep Alive, essentially a method for monitoring the health of a switch and to determine if any problems have occurred. So for example, if a core was lost or if a thread died. So it's an important feature for service assurance that's also being worked on for 2.7. And then finally, there's a configurable queue sizing. This will be available for 2.7. This allows the user to specify the number of RX and TX descriptors for use in a physical DPDK device. And so as far as I know, all of the above bar TSO currently have at least one initial proof of concept patch, an RFC, that's available on the OVS mailing list. And so if anybody is interested or has feedback, I highly encourage you guys to go on the mailing list, review these or try them out, and just give us feedback for any changes that could be required or anything you could think be useful. And so on that note, I guess that's it. So thanks everybody for taking the time to listen to this talk. I think we have questions lining up now, so we have some time to actually answer and go through some of them. So let me just work through some of these now. So I guess some of the more simple ones now. Okay, so how big a performance drop would be hit? How big a performance increase is seeing when using the NUMA Awareness feature? So I think we're looking for a 5% increase in raw throughput in the example that we actually presented here. how much performance decrease can be expected in using the pdump feature. So from our initial testing, what we found here is that this is about half, essentially. Okay. Can OVS DPDK be configured for jumbo frames and QoS from the guest? For that, does the guest has to be DPDK-enabled NIC or normal virtual NIC? So I guess just with this question, can OVS DPDK be configured for jumbo frames and QoS from the guest? Jumbo frames, potentially. I haven't developed the code myself. QoS, I know, no from the guest. QoS has to be configured from the host side, i.e. from the vSwitch side. Jumbo frames, there's certainly some configuration to be done from the guest point of view in the interface, but I suspect also if you want the packets to travel completely, i.e. you have packets coming from a virtual interface down and going out over a physical device, you will also have to do some configuration of the physical device also from the host side to make sure that the MTUs for the virtual port are going to match the physical port. Which OpenStack release will have the OVS 2.6 as default OVS release? I'm not actually sure on this one, to be honest. I think the way OpenStack work is they can take a commit ID essentially to work instead of releases. Now it depends when you go to the commercial OpenStacks. I know they use specific releases, but I can't actually answer that one off the top of my head. That's something I can investigate and I can answer back. Or feel free, if there's anything else here that I can't answer, feel free to choose a mailing list or tag myself, email it to myself, and I can come back to you guys and answer that. So, are there any QoS types supported besides Egress Policer? Currently, no. So currently, Egress Policer is just given as a sample implementation. I realize if using kernel OVS, you'd have implementations such as HTB and HFSC. Essentially, we're kind of like the idea of this that you'd be waiting on maybe a DPDK implementations of one of those kind of algorithms before it would be introduced. So just currently, the idea behind the work we did was just to introduce the flexible API, and just the Policer is kind of a simple sample app that was quite useful. So currently, no. Here's another one. Is there a performance impact for using QoS Policer? Yes, there is. If you're using QoS, I guess what you need to be aware of is that OVS DPDK is a run to completion architecture. So essentially, the RT meter, which we use for QoS, or the Egress Policer, that's CPU bound. So what you're introducing now is a new step in the data path where it must do some policing. So what we actually found in our testing was that the performance drops varies from port type to port type. But for physical port type, we would expect a drop of your maximum bandwidth, a drop of 22% essentially. So you'll still be able to achieve 78%, but that 22% will be spent on doing the policing itself. And for virtual ports, we got a drop of, I think, 16%. So is another one, what is the maximum MTU configurable? So I think the maximum configurable is 9710 bytes, essentially. That's actually the maximum configurable currently. And that's kind of defined, from what I understand, that is actually defined by the physical device, and the physical devices tested here were the XL710s, essentially. So, debug. So just looking through now. Okay, so the NUMA memory will also depend on which socket the NIC is connected, and not only where VM is hosted, right? In that case, we'll still need to pass the data through the QPI bus. How is this removed by the new change? So if you are connected to the wrong socket, then yes, traffic will still have to go over the QPI bus. I guess one of the bottlenecks that you're removing here is that at least the memory now is on the same socket. This is the type of question I wish Ciara was here. She could probably answer a bit better than myself on this. But you're right. If the NIC is connected to the wrong socket, you still have to go over a QPI bus. But that's if you're going over a NIC. You could also consider a situation where you just have east-west traffic to VMs, where you're not going over NIC, you're on the same system. So that could be a situation you could also be useful there as well. at the top, what performance packets per second can we expect when using OVS DPDK with 64-bit packets? So from what I'm aware, let me see. So this is an interesting one. We're actually in talks at the moment of releasing, potentially releasing nightly build results. And these results will show these performance. I know from testing myself, roughly, I think it obviously depends on the CPU you're using. It depends on the NIC you're using and the hardware offloads that are available there. So it will vary from system to system, but we would expect near line rate. So near if it's 64 packets, you'd be nearing 13 to 14 million packets per second for just 5 to 5 64 packets. Now, depending what you start putting on top of that, obviously you could have changes. But that's just a rough guideline. What I would suggest is that in the next few weeks, we're looking at doing proper nightly builds and releasing results. That would be a good area to consult. Question. Historically, when using DPDK-enabled application, it was difficult to debug. So the host OS had limited tools, guest OS had no tools, OVS limited. What tools and features are available for DPDK sockets apart from the new PCAP, which is great? I'm honestly not sure from the DPDK side, to be honest. So I may have to come back on this question. But again, any questions here, feel free to forward my own email, and I'll do my best to come back to you guys on that.
Thank you, Ian. I think that looks like that's the end of our questions. If you guys have any reference to any other materials you'd like to look at, you can see that we have a list of collateral available, and that the links to this collateral will be available in the recorded version, which will be available in a couple of hours. Actually, Ian, we have we might have a few more questions coming in. Do you want to review those, or I have a list of all these questions that I can send to you that you can get back to our audience.
Yeah, I can just review some of these. I think there's one or two more just after coming in. So yeah, one is related to benchmarking data, and we have performance number comparison for various packet sizes and compared to previous baseline Intel CPU. I'm not sure if we have baseline CPUs. We should have performance packets improvements as regards to different packet sizes to the current CPUs. Again, this is ongoing work as part of the OVS mailing list. This should kind of have an answer to this. I would expect within the next 2 weeks whether this is going ahead or not, and hopefully that's helpful for that situation.
Okay, well, I think this was a really good presentation, Ian. I appreciate your time, and I appreciate our audience's time. Again, all of this collateral will be available in the recorded version. You can just click on the attachments and links, and you'll have access to all the collateral that was referenced. And I hope everybody has a great day. Thank you.
Yep, thanks, everybody.